So part 2, the types of bonds. There are two major types of bonds that hold atoms together. So if you think about a molecule of water, water you know is H2O. H2O. That means that there's 2 hydrogen and 1 oxygen. So 2 hydrogen and then there's 1 oxygen. Now these hydrogens are going to have to bond with this oxygen, and that's what makes one molecule of water. So when we want to make anything molecular, we have to form these types of bonds. And there's 2 major ways that molecules will come together to form bonds. There's ionic bonds and covalent bonds. An ionic bond is formed between a metal and a nonmetal. So if we look at the periodic table of elements again, the metals are pretty much all of these. The nonmetals are these guys. And then you have metalloids that exist in between here, which have properties of both the metals and the nonmetals. We're not going to worry about how they form bonds in this class because this is a biology class and not a chemistry class. But for the most part, ionic bonds are formed between a metal and a nonmetal. And when they're formed, the metal usually loses electrons, while the nonmetal gains electrons. So the metal gives them up, and the nonmetal accepts them. When the metal loses electrons, it becomes more positive, because remember, electrons have a negative charge, so if you're giving up negativity, you're becoming more positive. So the metal becomes the positive one. And when you gain electrons, you're gaining negativity. You're becoming more negative, so you gain a negative charge. So if we had sodium to start, sodium would become +1 or 1+. Because it has a positive charge, this is known as a cation. The way that I remember cations have a positive charge is I'm like a crazy cat lady. I love cats. My husband probably loves cats more than I do. But anyways, so cats make me happy, positive, positive, cation. Cats are positive, cation, positive charge. We have the nonmetal, which becomes negative. So for example, if we had chlorine, and chlorine gained 1 electron, it would become negative by 1, which we put 1 negative. And now we call it a chloride ion. This is the anion. And this is important because ionic bonds are held together due to opposite charges attracting. So this positively charged cation stays near the negatively charged anion because they happen to be oppositely charged. The positive charge gave up its electron, the negatively charged one accepted it. Now let's draw out how this is actually happening. So we drew out sodium earlier. Instead of drawing out all of the shells of sodium, we can just draw out the valence electrons. Now how do we determine the valence electrons? If we go back here, we said anybody in this first group has 1 valence electron. So sodium is going to have 1 valence electron. So for sodium, we're just going to put 1 dot here. Now sodium is going to form a bond with chloride. And again, for chlorine, we're just going to draw out the valence electrons. So if we look here and try to find chlorine, chlorine's here. Chlorine is in group 7. So there's 7 valence electrons. That means that there's 7 electrons in the outermost orbital. So 1, 2, 3, 4, 5, 6, 7. Now what I like to do when I draw these out is I pair them up. So I put 2 next to each other, 2 next to each other, 2 next to each other, and leave that one by itself. So when I'm actually distributing electrons, I'll go clockwise once around, 1, 2, 3, 4, 5, 6, 7. And then I'll follow it up with that second around so that we end up with the appropriate pairs here. When you see 2 electrons that are next to each other like this in pairs, these are not going to form bonds with anything because they're already married. So these 2 are married, they're not going to form bonds with anything else. These 2 are married, they're not going to form bonds with anything else. Again, those 2 are married to each other, they're not going to form bonds, but this one's single. So this one wants to get married. This one is single, so that one wants to go over here and become married. So we're going to give up this electron, bring it over here. Sodium just lost its electron, and we put brackets around it and make it a +1 or a 1+. The chloride ion just gained that electron, so it took something from sodium. So we draw all of the outer shell here filled up, and we indicate that it took an electron by putting a -1. So this is how we express ionic bonds. If we were to actually draw what we call the Lewis structure of an ionic bond, this is what it looks like. We keep brackets because they're not physically connected to each other. They're just hanging out near each other because opposite charges attract. Believe it or not, some metals are more attractive than others, which sounds kind of funny, but they're considered more active. It's easier for them to give up electrons, which again, we can get into some pretty funny topics on giving up things. But anyways, so as you increase in atomic number, you're adding more and more orbitals, which makes it easier for that lone electron to go away. As we go down here, they become more reactive. They increase their activity level as they go down. So chloride is going to be more excited interacting with potassium than it would be interacting with something like lithium. So we do have kind of an activity series here. There are more and less attractive cations to interact with. So for this class, you need to know the basics of the ionic bond. So again, it's a metal to nonmetal. The metal loses electrons, becomes positive, and that makes it a cation. The nonmetal gains electrons and becomes negative, and that makes it an anion. We can draw out magnesium bromide as our second example here. Magnesium bromide is MgBr2. So we draw out magnesium once, and we have to draw bromine twice. If we go to the periodic table, magnesium is in the second row. So magnesium has 2 valence electrons. Bromine is in row 7 again, just underneath chlorine. So we're going to draw 2 for magnesium, but each bromine is going to have 7. Now this one can go to this bromine, this one can go to this bromine. So in the end, magnesium has a +2 charge, and then each bromine would have a full outer shell, bracket -1. You won't have to draw these out on an exam or on a quiz, but you need to have this foundational knowledge of how bonds are formed, and this is how ionic bonds are formed. Now these ions are going to float around each other in solution. So if they were mixed in water, they would be floating all over the place. That is what an ionic bond is. It's weaker than the next bond that we're going to talk about because it's just held together because opposite charges are attracted to each other. Now we're going to focus on the covalent bond. In a covalent bond, usually exists between two nonmetals. There is an equal sharing of electrons. And they're extremely strong. It's almost impossible to break up a covalent bond. If you want to think about this like a dating relationship type thing, ionic bonds are kind of like dating. So they are opposite in some way, whether they're opposite personalities or opposite sexes, whatever. They're opposite in some way, so they happen to be hanging out near each other. But as soon as chlorine finds a more attractive metal, it's going to ditch poor sodium and go hook up with potassium. So it's not like these are sharing anything. Chlorine took something from sodium, and as soon as chlorine gets bored with sodium and finds a more exciting metal that comes along, more exciting ion or cation that comes along, it's going to give sodium back its electron and go get that electron from that more exciting one. So it's kind of a weak dating relationship. But as soon as you have a covalent bond, this is a marriage now. So we have an equal sharing of electrons. In a marriage, you share everything. And these are very strong. It takes a lot of energy in order to break them apart. So we'll draw out some examples of covalent bonds, starting with what water looks like. So water, again, is H2O. With covalent bonds, you usually want to have the one with the higher electronegativity or the one with lower numbers in the center. So since we only have one oxygen and we have two hydrogen, we're going to put oxygen in the middle. And then we're going to put these hydrogens around the oxygen. So we're going to assign the same electrons that we did with the ionic bonds. So oxygen is in row 6, so oxygen has 6 valence electrons. So we're going to do 1, 2, 3, 4, 5, 6. Now we look at hydrogen. Hydrogen is in group 1, so each hydrogen has 1 valence electron. 1 and 1. Now for covalent bonds, we play connect the dots. So these are going to be shared with each other, so we connect those and form a solid line bar. These are going to be shared, so we're going to form a solid line. So that's basically what the structure of water looks like. So we have, if we want to draw it a little bit better, that would be our final structure of water. Now water we're going to learn about the properties of in just a little bit, but water is unique in that it's a polar molecule. So when you have this polarity here, the oxygen is an overall negative charge, and each one of these hydrogens kind of forms an overall positive charge. Even though they're bonded together like this, kind of a different type of pull toward a negative charge toward this oxygen. So hydrogen is a very polar molecule, and we'll learn more about hydrogen or water's polarity once we get into the next section. So let's look at another example here. So another example would be CH3OH. So we're going to draw a carbon with 3 hydrogens around it. Now we go to carbon here. Carbon is in row 4, so we have 4 dots around carbon. Each hydrogen has its own dot. And then we're going to draw an oxygen. And if you recall, oxygen has 6. So 1, 2, 3, 4, 5, 6. And then hydrogen has 1. And now we're going to marry anybody that can get married. So these guys are going to get married. These guys are going to get married. These, and these. We don't want to marry these two to each other on the same atom. Because if you think about this as a family and you're trying to marry off all of your, brothers and sisters and everything, if these two got married, that would be incest. So we don't do that. So now we've formed all the bonds that we can possibly form, and we have our actual Lewis structure, our actual molecular structure of what CH3OH would look like. This is methanol. Here's the alcohol group, here's the methyl group, and that's what methanol looks like. That's methyl alcohol, methanol. But anyways, so now you have an idea of how these bonds are formed and how they come together. And breaking one of these is nearly impossible. It requires a large energy input in order to break those bonds. The last type of bond that I'm going to talk about today is hydrogen bonds. So hydrogen bonds, also known as proton bonds, hydrogen bonds exist between the overall kind of positively charged hydrogens and an oxygen or nitrogen, something that's electronegative, on a neighboring molecule. So they're not covalently bonded together. The hydrogen is interacting with this oxygen on this other molecule. These hydrogen bonds allow water molecules to stick to each other to form surface tension, and that's why those small insects can climb on the surface of water. And we'll learn more about the properties of water in just a little bit. But hydrogen bonds, again, exist between a hydrogen and a neighboring electronegative atom that's bonded, covalently bonded to something else. So this is not a covalent bond. It's pretty weak. It's just an interaction that happens. But it's not too weak. Our DNA, so DNA that's inside of our cells that stores all of our genetic material, all of our genetic information, DNA is made up of 4 bases: adenine, thymine, guanine, and cytosine. And of the 2 strands of DNA, if we have an A on one side, it's going to have a T on the other side. And those bases pair up down the middle. We'll learn more about the structure of DNA, but here you can see this is the backbone of the DNA, and then these are the bases that are coming together. Thymine is bonding to adenine, guanine is binding to cytosine. In the middle here, these are all hydrogen bonds. So hydrogen bonds holds the 2 strands of your DNA together. And that's going to be important later when we explore the structure of DNA.